Hello guys, and welcome back to my YouTube channel. In this video, we're going to be going over an intramolecular reaction. Once again, before I get into the content, please make sure to leave a like, comment, save, and or subscribe to my channel if you like my content and you find it helpful. That would be appreciated very, very much. Okay, let's get into the video. Step 1 of every reaction ever, you have to find your nucleophile and find your electrophile / the electrophilic carbon, so any carbon with a leaving group. Let's attack finding the nucleophile first. Here we have NaOH as a reagent. Whenever you see an Na, assume it is positive, and whatever it is with, assume that it is negative. So here we have an OH minus, and we pretty much can forget the Na exists. So an OH minus, this is a base. Bases want to attack hydrogens. So which hydrogen is this OH group going to attack? A really good candidate would be a hydrogen attached to an oxygen. So looking at our compound, can we find a hydrogen attached to an oxygen? Yes. Okay, it's right there. So let's say the base goes to N, I'm nucleophilic, I'm going to attack you because you're a hydrogen and you're delta plus and you're attached to a delta minus electronegative oxygen. To N, to up. So the oxygen is going to gain those 2 electrons in the OH bond and become negatively charged. So let's draw our, oh wait, this would be the conjugate base. Let's draw the conjugate base of this structure, where you are pretty much going to draw the exact same structure except the atom that had the hydrogen stolen from it. All that happens is it becomes negatively charged. So this oxygen is going to now be negatively charged. Aha! Okay, we've found our nucleophile because nucleophiles are nucleus loving. So if they love positively charged things like the nucleus, then they have to be negatively charged. Wait, nucleophiles are negatively charged? Yes. We found our nucleophilic atom. Okay, now the question is, who is it going to attack? Now there's going to be 2 potential candidates. You have to look for carbons that are delta plus or carbons with a leaving group. For example, halogens. Halogens are amazing leaving groups. We have a halogen right there, chlorine. And then we have a carbon attached to an oxygen, a carbonyl carbon over there. So the carbon attached to the chlorine right there and the carbonyl carbon are both potential electrophilic sites that could be attacked by this nucleophilic oxygen. So now you have to figure out which carbon is most likely to be attacked. Sterics always plays a role in every single mechanism ever, okay? So I hope you could see, and if not, that is always okay, that it would be very inconvenient for this oxygen to go and attack that carbon. If you think about the path length, okay, draw the first arrow, the arrow towards the carbon, a part of the carbonyl in white, and a second arrow towards the carbon with the chlorine group. Which one is shorter? So think a shorter distance, because atoms don't want to expend all of their energy, right? They're just like us. Consider yourself. Let's say there was 2 bakeries near your house. The one bakery, bakery number A, is a 10-minute walk, whereas bakery number 2 is a 40-minute walk, bakery number B. And let's say in this hypothetical situation that both bakeries make really good muffins. Which bakery are you going to choose to go to? Let's say it's a really cold day too. It's not the best day to go out for a 40-minute walk and you're busy, right? You have school, you have to study for your tests. Which bakery are you going to go to? The one that takes you 40 minutes to get there or 10 minutes to get there if the result is going to be the same thing? At both bakeries, you're going to be able to buy a really good tasting croissant. You would probably end up choosing the bakery that is closer to your house because it's going to take you less energy to go there and get the final result, which is you buying a croissant and eating it. Nucleophiles behave the exact same way as you in a situation like this. They want to attack something that is electrophilic, so a carbon. They're going to choose the one that's easier to get to. So this O- is going to attack the carbon attached to the chlorine group. So that carbon right there. So now we've established our nucleophile. We've also established the carbon that it's going to attack, so the electrophilic center. Now we just have to draw in all the arrows, so we got to do the mechanism. Okay, this is going to be step 1. We have already established that the first arrow is going to be drawn from the nucleophile to the carbon with the leaving group. So now, does the leaving group just leave? Do we have a 2 out right away? The answer is actually no. In the very end, the leaving group is going to leave, yes, but whenever there is pi bonds that can resonate, aka hang out with one another, resonance always occurs first. Pi bonds are easier to break than sigma bonds. So the electrons are going to resonate with one another. The electrons are going to move towards the atom that wants them the most. So what atom wants them the most here? Well, it's going to be this oxygen. That's delta minus. And then you're going to get an intermediate structure. And then after you get your intermediate structure, we will then make the leaving group leave. But first we have to draw our intermediate, where we have a 2 in, 2 over. Oh wait, this group can accept pi electrons as well. So we have another 2 over, and then we have a 2 up. When you follow the electron flow to figure out which atom becomes negatively charged, just follow the pi bonds, follow the path, and then the last atom, here, the atom that is the oxygen atom, will be the atom that gains a negative charge because the electrons flowed towards it. And if you gain electrons, you become negatively charged. Gen. So drawing the result of pushing these arrows. The best way to do this, so draw intermediate structures that are quite complicated, so you got to draw in a lot of groups, is draw in all the things that didn't move first. So your benzene group on the left-hand side stays put. There's also a bond to an oxygen. Then this carbon is bonded to 2 carbons. The oxygen is now bonded via that blue arrow to the carbon with the chlorine group. Now go atom by atom. So now this carbon, let's label it in green, is going to be connected to another carbon. And then these 2 carbons are connected to one another. Draw in the rest of the other benzene ring. Label those carbons. This is arbitrary, 1, 2, 3, 4, 5, 6, just so you can track where the electrons are going to go. So we see the head of an arrow is pointed in between atoms 6 and 5 via this labeling. So put a pi bond in between atoms 6 and 5. We see the pi bond in between atoms 2 and 3 did not move, so keep it there. Carbon number 4 is connected to the carbon with the carbonyl group, so draw in the carbonyl group, but now the oxygen is going to have a negative charge, and we can also see that we have the head of an arrow in between carbon number 4 and the carbon, a part of the carbonyl. So another pi bond also is going to exist right there. And there we go. That is our intermediate structure. And I promise you we are almost done. So now the final step is the leaving group must leave. And the aromaticity of the benzene group also needs to be reestablished. So now what you have to do is you have to start at the negative charge. So now the purple oxygen right here. So starting at this oxygen via 2 in, 2 over, 2 over, 2 out. So they go in the exact opposite direction as they came on the way in when the ring was formed and we got our intermediate structure. So now all we have to do is draw our final product. Once again, draw in everything that did not change first. So this benzene ring didn't change. And the new ring that we formed also did not change. So that ring did not change. We also know that there's a benzene still. Put the pi bonds in between the atoms where the heads of the arrows are. So now there's a head of an arrow. And then the pi bond in between atoms 2 and 3 did not change. Right there, and right there. That one didn't move. And then redraw in your carbonyl group. This would be your final product. And then you have your chlorine minus. Oh wait, there's also an Na plus in solution, right? So you get NaCl, and you have H2O. Bada bing, bada boom. I hope this was helpful. This was just a practice question example. Let me know if you have any questions in the comment box down below. I hope this video was helpful, and I hope you have a great day. You guys have got this. Keep on studying and keep on watching these videos. Make sure to leave a like, comment, save, and or subscribe to my channel if you like my content. Have a great day. Bye.